So the question is, are we defining this as positive work, or are we defining that as positive work? So I think that's the broader question is, if we have a force and a displacement in the same direction, that's positive work. If we have force and work in the same direction, that is positive work. So we can have positive work with both a force in the left or the right or the up or the down direction, provided the displacement is in the same direction. When we're talking about a piston system or any gas in general, the question is, what is positive work? The gas is exerting a pressure and a force pushing inside the cylinder, pushing up on the piston. There's gas outside pushing down. So if the piston moves up, there is positive work done by the gas inside. We're defining this as our system. And there's negative work done by the outside world. So it depends on what we're saying is doing the work. Are we talking about the gas doing the work? So is the gas inside our system doing the work? Or are we talking about the external world? So the work can be positive, done by the gas, or it can be negative, done by the gas, depending on whether the volume is getting larger or getting smaller. And we have work done by the outside world with the opposite sign. So there is the possibility for a lot of confusion here. So the question is if we look at the integral of our PVD diagram, and our process is from left to right, is that positive or negative work? And the answer is yes. But it depends on what you're talking about. If we're talking about the gas doing work on the outside world, then we will say that that is positive work. If we're talking about the work the outside world does on the gas, that is negative work. What's that? Oh, never mind. Okay. Because now the force is on the opposite direction on the piston. So the volume is getting larger. The volume of the gas inside. Presumably, in some sense, the gas in the outside world is getting smaller. It's a little harder argument to make. Certainly this gas is expanding, its volume is getting larger. If we talk about the work done by the gas, it's positive. If we're talking about the work done on the gas in the cylinder, it's negative. Does that answer the question? Now, what does that have to do with which work am I talking about there? By exact dimension, we will see both of those equations. This convention is work done on the system. This is done by the system. Now for heat engines, we can rearrange this equation here. So the engine we're interested in what work is done by the system. And we can rewrite that as Q equals D, our change in thermal energy, plus now our work out, or our work by the system. And we started to talk about the fact that this heat, as we go around the cycle, there will be certain stages, certain of those processes as we go around our cycle where there is heat coming into the system. And by the second law, that will be coming from the hotter reservoir. And for our engine, there'll be certain cycles, processes in the cycle where there'll be heat going out. And so we can rearrange this to Q hot minus Q cold equals E delta E thermal. Our change in our thermal energy plus our work out. But if this is a closed cycle, what do we know about the thermal energy of the full cycle? Zero. It doesn't. There's no change in the thermal energy. So the change in thermal energy over a complete cycle is zero, and our equation becomes Q hot minus Q cold equals work. So what we'll do is we will say that there's some hot reservoir, and we always put the hot reservoir on the top. We'll have some cold reservoir at the bottom. We'll have some energy as heat coming down from that hot reservoir. We'll get some work out of our cycle, and then there'll be some Q cold.
What does your label the bottom arrow?
Let me draw that a little bit larger. This is a rearranging our first law of thermal. So it's the same thing we've started out with. We've started out with our first law of thermal. And we've defined work out because we're creating an engine. We're going through a complete cycle on our PV diagram. So there's multiple processes, usually 3 or 4. So our change, is there a thermal change in thermal energy in any given process? So if we have an adiabatic process, would there be a change in thermal energy? Yes. The adiabatic, there's definitely a change in thermal. If it's isothermal, there isn't. An isobaric or isochoric process, there is a change in the thermal energy. But if we go through a complete cycle, in one complete cycle of our engine, and if this is an engine, is this process clockwise or counterclockwise? We have to have positive work out, so we have to have more area under the curve when we're integrating from left to right. So that would be an engine. And we'd stop at any one point. If we go through a complete cycle, we'll always have the same thermal energy at that point because we have the same temperature. So through one complete cycle, this is 0. Therefore, Q minus work out, or work by the system, is equal to 0. We can rearrange that to Q equals our work out. But since we're a closed system cycle, our change in thermal energy over cycle 0 will change our Q into what's coming from the hot reservoir and what's going to the cold reservoir. We can draw that graphically as this. Now, if we get 100 joules from the hot reservoir and 50 joules go to the cold reservoir, and I tell you that we're creating 60 joules of work in this engine, do you believe me? No, that would be a violation of the first law of thermal. So that's a lie. What, in fact, would be the workout? 50. So there's some fairly complicated math behind all these processes, but when we describe it as a heat engine in this format, it's pretty easy to understand. You can very quickly look and say, have I violated the first law? We'll also talk about, did we violate the second law? We'll practice that today. So it's a very nice lead-in to today's lecture. We'll both finish last lecture, which is really this discussion. The sign convention is you have to be careful. We accept both of these, read the problems that I give you. It's like the whole thing with the electron, where I begged you to be very, very, very careful with electrons. I beg you to listen very carefully. Which work are we talking about? Work on the gas or work done by the gas? All right, let's go through this. So our heat reservoir, we talked about those. We think of a heat reservoir as like an ocean. An example in the textbook, you drop a hot rock into the ocean. What happens to the temperature of the rock? Cools down. What happens to the temperature of the ocean?
Nothing.
Yeah, in theory it goes up a little bit, but yeah, do you really believe you're going to look at your thermometer and change? Not really. That is a cold reservoir. The ocean, we're going to assume, is pretty much the same temperature, at least in one place. If you go to Hawaii, it's much warmer than it is in Puget Sound. So in heat engine, we are extracting work while energy is transferred from the hot reservoir to the cold reservoir. That picture makes sense. We'll do some examples that hopefully make this work better. We will study closed cycle engines. So the process is repeated again and again. We're going to assume that the number of moles of gas involved does not change. And that keeps our analyses more straightforward, but it gives us a tremendous amount of insight into the processes. The thermal energy at any point in the cycle is the same. So if I come to this point again and again and again, E thermal is the same. Why? Every time I come to this point, under these conditions, why is the thermal energy the same for our system? Temperature hasn't changed. E thermal is a measure of the internal energy. Temperature is a measure of the internal energy. If the temperature is the same, the thermal energy is the same. I've repeated that lots of times, haven't I? I'll ask some variant of this. Almost undoubtedly in the multiple choice questions. Even with all the warnings, people will miss it. Please don't be one of them. All right, we went through the math, we've gone through the math there, and here is our drawing. So our heat engine is inside, our system's inside here. We have the hot reservoir, heat comes in, work out, heat out. Now, the first law of thermal says that work out equals Q hot minus Q cold. Everyone see that visually? I also said that the efficiency is less than or equal to 1 minus T cold minus T hot. It's also also equal to what we are getting, work, out, divided by what we paid for, QH. So what is the efficiency of this engine here? We're getting 50 joules of work. In general, we're paying for a QH. Our efficiency, therefore, is 50%. Does this violate the second law of thermodynamics on this engine? Well, is T cold so 1 minus 30 over 700, that is definitely, so that's 3/7, that's equal to, it is 1/2 less than or equal to 4/7. Yes, it is. That is not a violation of the first law. It's going to be the second law. If the temperature of the cold reservoir were 400 Kelvin, this would be a violation of the second law. So let's do some practice. This engine right here, I am beginning to really and this is practice. I'll give you a real quiz in the last 10 minutes. Three, two, one, and all right. Most people says it does not violate the first or the second law. Let's check. QH minus Q cold is 40 joules. 40 joules does equal 40 joules. So what goes in? 100 joules equals what goes out? 40 plus 60. Any questions about first law? What is our efficiency? We get 40 joules of work out for the 100 joules of energy that we buy from the hot reservoir. Our efficiency of the system is 40%. Is 40% less than or equal to 350 divided by 1,000? Is 40% less than or equal to 65%?
Yes.
Yes, we have not violated the first or second law with this engine. This is, whatever this engine is, it's theoretically possible. Isn't that exciting? You just evaluated an engine. All right, let's look at the next one. I don't know if the designers are as good on this one. What are the chances? the first law violated?
Oh, we already went through this.
See, we have 100 in, 40 plus 60 out. I don't know what our options are.
I think that's the same
problem.
problem.
Yeah, this is the same
It's a breakdown
problem.
why it doesn't violate you.
Oh, there you go. Let's, yeah, take down more. Let's go to the next one.
Same one.
All right. We've kind of sorted that one out.
What? Oh yeah,
Oh,
this
this
one's
one is
different.
different.
Yeah,
So I've given you the answer, I think. Three, two, one, and done. So, this is a lot nicer engine. We get 60 joules workout for the 100 joules we're paying for. So we're a lot happier. We're getting 60% efficient. We haven't violated the first law. We're not getting more out than we put in. But we've cooled down the hot reservoir. We haven't changed the cold reservoir. And let's see. Is 60% less than 1 minus 350 divided by 700? So it is 60% less than or equal to 50%. No. No, we have not violated the first law, but we have definitely violated the second law. This is not, theoretically not possible. Even though the energy is conserved, what comes in goes out. The second law of thermodynamics, if we understand the entropy, we just cannot build an engine that works this way. It's not theoretically possible. I wrote the computer. I will see on that. This is yet a different one. Excellent. So, what goes in is 100 joules, what comes out is 90 joules. So we have 10 joules of energy disappearing in the universe. It's a no-no. In thermodynamics, we've definitely violated the first law. What is the efficiency of this engine? You get 30 out for 100 in, even though 5 is missing, or 10 is missing. So our efficiency is 30%. Our maximum efficiency is, in this case, 350 over 1,000, or 65% maximum efficiency. That golden reservoir. We've definitely not violated the second law. Even if you added that 10 missing joules to the workout, we're still not violating it. Any questions about that? Should we do one more? Oh, this one's much more interesting. Now, we're actually looking at the cycle. So can we analyze this? So rather than going to this format, what if we started from here? Could we fill out that work diagram? Can we do the same analysis we've done by now looking at the cycle on a PV diagram? So what kind of process do we have from here to here? Good, isochoric from here to here. And this one? No idea. It's kind of neat, it makes our math easy, but we do, let's see, we don't know the hot and cold. So we can't look at the second law. We can't, let's analyze the first law here. What work is done by this system? Can we figure that out? First of all, is work done by the system or done on the system? By. It's a clockwise process. The work is done by the system. How would we find out the work done by the process? We could find the integrals of those three processes and find the work of this process plus the work done by this process minus the work done there, or adding the negative, depending how you think about it. But the easy way is just to find the area of the triangle, isn't it? What's the area of that triangle? I would say, see, the height change in pressure is 200 kilopascals. So we have 400,000 minus 200,000 pascals times, what's our change in volume? 200 cubic centimeters minus 100 cubic centimeters. And then this is a triangle, so we have to divide by 2. Now there's some unit issues here, aren't there? What is a Pascal? Bad joke.
Newton.
1 meter squared, 1 Newton per meter squared. And let's see, if we're going to get rid of centimeter, if we're going to turn to joules, we need Newton meters, not Newton centimeters. So, are there 100 centimeters to a meter? Are there 100 cubic centimeters to 100 cubic meters? 100 centimeters does equal 1 meter. We need to cube them. There's actually 1 million cubic centimeters in a cubic meter. So now we have meters squared canceling with meters cubed. We have Newton meters. 1 Newton meter equal to 1 joule. So the area is the easy part. The unit analysis is a little bit tough, but not bad. Very manageable. That equals well, what good is that? We do know now, if we go up here, this is 10 joules. Do we know Q hot or Q cold yet? We know that there's one more Q here. We know that that's negative work done by the system. We have 84 joules here. We have 30 joules here, right? So those are both heats in. So how much heat in do we have? So far we have 114 joules in. And we have 10 joules out. Well, that tells us QC has to be what? Does that make sense? Is this a terribly efficient engine? No. But if I had drawn that and I asked for the efficiency of that engine, I think all of us would at first have said, we can't figure that out. But if we do, we can calculate the work. We know a delta E thermal for the cycle is 0. We know the heat for 2 of the cycles. We know the work out. We should be able to find the heat for the 3rd cycle. How many people think if I gave a problem like that on the test, we could do it now? How many people think we maybe need a little more work? We'll do a couple more examples. Alright. So, there is homework due tonight. It's mostly gas laws. I may delay that a little bit. I may have already delayed that. These are our last 2 assignments. I do have a workbook assignment for Wednesday. So this will be chapter 19, 1 through 19. And this is it for our homework. I believe we're at the end. Alright, you guys ready for a real quiz? Before I do it, any questions about gas law, ideal processes, what makes it, what assumptions we have for our ideal gas laws? This is not what we've just done. I'll have a quiz Wednesday over the stuff that we did today, so very much like the quiz of today. This is more like what we've done last week.
What does the gas have to be like to be nice gas?
Ideal gas. So for an ideal gas, what are the assumptions? That is an excellent question. Everyone thank Travis. All right, 4, an ideal gas. What do the gases have to be? We want the molecules to be far apart, but we want the statistics to be good. We want them to collide inside. So we want the density to be low, right? The pressure is low, and we want the temperature to be high. That makes it, got it? So that is our second question on this quiz.
We also went in quasi.
Any other questions before we go? That's not what I wanted to do. Operator error. What kind of process is this? Sure. Cannot be sure. Thank you. Don't be fooled. 93% of you were not fooled. That's good. Thank you, Travis. Thanks, Travis. Good man. Travis, you help us. heavily insulated mean?
No loss of heat.
Means there's nothing, something that's not escaping the system. Three, two, one. All right. What type of process is this? Adiabatic. So the work done on the gas is positive, the work done by the gas is negative. What happens to Q is 0 because it's adiabatic, it's well insulated. So if the work done on the gas is positive, then delta thermal must also be positive, so the temperature must go up.
No.
Oops. Oh well. Next question. That is next question. All right, let's get 100% on this. Everyone, the answer is B. I will score it. Stop. 3, 2, 1, stop. That is what I hope would happen. All right. That's an attendance grade.
That's it.
All right. I want to quickly talk about why some of this is happening. And there are some really interesting relationships here. So, there are 2 more mastering physics questions. They're relatively straight problem sets. There we go. There's only 2 problems. And there's the mastering workbook. That's it for the class. There's a whole bunch of problems. I do want to go over this. I'm a little bit behind on our lecturing. But this is backwards from the way Knight has presented things, but I think seeing the big picture coming back to this and then starting to actually analyze the processes, tie in with engines and refrigerators helps to make sense. This is a little bit like the lab we did last week. So that's not there. Kinetic theory says that we can measure the average range of speeds in a collection of gases. So if we look at just a random collection of molecules at, say, 20 degrees Celsius, we get a bar chart of speeds for those different particles in that gas. So the molecules, we'd have very, very few really slow molecules, but there'd be some. You can imagine the molecules slide into it just right. Its average velocity is very low. But there's, and the very high, you can imagine sometimes things collide just right, and you'll get some very high speeds, but this will quickly collide with something and slow down. But at any given time, we'd expect a distribution of velocities. So all the little molecules that are shaking around, there's kind of some fun YouTube videos of particles shaking around and on pool tables, and we can get one. They're kind of fun to look at. But you can see that all the different molecules, or in the case particles, on the pool table, they are not traveling the same speed. There's a distribution. The temperature is the average temperature. It's the average energy of those molecules. So we're really talking about things in a statistical sense. Now there's some very, very interesting predictions from the kinetic theory. And that is that the number of degrees of freedom, in other words, the number of ways a particle can move, are 3. It can move in any of the 3 dimensions. If we have a diatomic gas, it can move, it can rotate, it can shake, it can rotate, or it can move in any of the 3 directions. So it has 3 degrees of freedom. So there's different ways for that molecule to have energy rather than just moving in the 3 dimensions. And then in elemental solids, there are 6 degrees of freedom. It works out that the specific heat of those molecules depends on the different ways they move. So the more ways they can move, that greater the specific heat of that substance. So it works out that monatomic gases and diatomic gases have different specific heats. Now, the specific heat there, I called CV. Why did I just call it the specific heat C? If we go back to our gas situation, there's many different ways that we can heat our gas up. But two possible ways of heating the gas are, we put the locking pin in, and as we add heat to that gas, the temperature will increase, there's no work done. The gas just heats up. There's no work done. If, however, we keep it unlock the pin, keep the number of masses on the top of the cylinder, as we heat the gas, now it's at a constant pressure, we get a different specific heat for the gas, because now work is being done as we add heat. So it actually takes more heat to increase the temperature of that gas, because some of that work and heat is actually going to work. So we'll talk about two different specific heats. The specific heat at a constant volume, or CV, and the specific heat at a constant pressure, CP. And it works out that they are related to the ideal gas constant, R. So macro behavior, we can predict the behavior of gases by statistical description of the molecules. And the temperature is a measure of the average energy. We can explain pressure by the average number of collisions with the wall and the change in momentum with the wall. Remember the impulse that we did? So we can look at the impulse and we can calculate the force from all those collisions, the change in momentum. We can talk about heat, explain heat capacity. But there are some very odd facets of gases' behavior. Some diatomic molecules act like monatomic molecules at low temperatures. And then there's a transition as the temperature goes up. And they start to act from more like true diatomic molecules. So, again, our ideal gas laws do apply at low pressures, high temperatures. At low temperatures, higher pressures, weird things happen. We're not going to be able to go into that. But as a warning, these models do fall apart at higher pressures, lower temperatures. Our first law of thermal is still there. This convention is the work done on the gas plus the heat added to the gas is equal to the change in thermal energy. And we can start to derive the second law. We can actually explain why the second law has to work if we go through the statistics. So I want to tell you the second law of this equation we had down here, it's not pulled out of thin air. There is a derivation out of the statistical mechanics. So, here are some questions. What good is the first law of thermal? Isn't the ideal gas law good enough? Right? What is the difference between thermal energy and heat? This is a source of confusion for a lot of students. What does well insulated mean? And how can two processes start and end at the same point on the PV diagram and have different rules? Is that even possible? If I have a process, and I go from, here's my PV diagram, and I go from this state to this state, don't they have this, doesn't this state always have the same temperature? Doesn't that always have the same temperature? Can I go from here to here two different ways and have two different heats and two different heats and two different works? Yes, I can. So, isn't the ideal gas law good enough? No. We need to look at the first law of thermal and the second law of thermal. What is the difference between thermal energy, or the change in thermal energy, delta E thermal, and heat? Is there a difference?
Yes.
Yes. Thermal energy is the energy in the system. It is a function of the temperature. The greater the temperature, the greater the thermal energy. Right? It exists when a system is isolated. So I can isolate a system. I can isolate it from the rest of the universe, and there still is thermal energy. What about heat? Heat is energy transfers, right? So it is from the outside universe to our system, or from our system to our outside universe. If we isolate a system, can there be any heat? No, because it's isolated. How do we isolate a system? Those are the two big keywords in this class. Well insulated or quickly. So that implies there's no heat. And the first law when there's no heat becomes delta E thermal equals work. Is that work done on the system or by the system? Going back to that sign convention. That would be work done on the system. So the temperature in a well-insulated system will change if there is work done on the system. And what do we call that process? Can two processes start and end at the same points on a PV diagram and have different works and heat? Yes. The ideal gas law is still part of our picture. I'm going to go through this really quick. We still have to look at work as the integral. What is this P? What does dV mean? We've done a lot of integrals. With respect to volume. It is not our change in volume. Our change in volume is from V initial to V final. It's telling us we're integrating with respect to volume. To evaluate this integral, we need to replace P with an expression for the pressure, where the only thing that's changing is the volume. And then we can evaluate that integral. But unless we know how P varies with respect to volume, then we cannot evaluate the integral. The dV tells us what we're integrating with respect to. The change in volume is in our limits. Finally, we need to look at the processes. We need to know what heat's involved, and if we know the work, then we can calculate the change in thermal energy. If we know the change in thermal energy, we can find the change in heat. How can we find thermal energy? If we go back to our lab, isn't change in thermal energy the heat capacity times the change in temperature? So we're going to do that very quickly. We're going to actually, I'll just set up and we'll take off on Friday. I don't want to rush this. What we're going to do is look at two processes, an isobaric and an isochoric process. Which one? There's definitely a difference in work, right? The isochoric process, there's no work. And the isobaric process, there will be work done by the system or negative work done on the system. Is the temperature change the same for those two processes? Is the change in thermal energy the same? Yes, the same change in temperature. Is the heat the same? No. So this is kind of interesting if you think about it. We're doing this two different processes. The temperature change on the same gas. The two different processes will require different heats. Even though it's the same gas going through the same temperature change, there'll be two different heats. So what we'll then do is we'll quickly go look at the first law, we'll evaluate things, we'll substitute into the gas law, and what we'll find out is the specific heat at a constant volume is less than the specific heat at a constant pressure. And the difference is the ideal gas law R. So we'll go over that on Wednesday. I don't want to rush through the process. But isn't that fascinating? So that's as much as deep as we're going to go into the statistical mechanics. It all kind of ties in, and what it tells us is these things, CP and CV, really are a function of our ideal gas law. And this is the strongest hint I can give to you that that's true, because I can show you that the difference between them is actually